Hi! As promised, the follow-up video to the mid-range SunFire systems. I wanted to say thank you, first of all, very much to everybody who commented, who sent me messages. It's really nice to know that people out there care. Sometimes I feel like what I'm doing is so ridiculously nerdy, nobody could possibly give a crap. And yet, 1,500 views over the space of a couple of days, clearly other people care, which is kind of cool. I guess we're all losers together. Everybody hug. So, I thought we would start with the 6800, which I have mostly dismantled, and begin with the inside, working our way out. Before I begin, actually, there was something that I learned last time. I said I didn't know the difference between the SunFire 4800 and the 4810. And the 4810 is effectively the same machine, but the chassis design is different, and it's designed for when there won't be convenient access to the rear of the chassis. And so everything, the controllers, the repeater boards, the system boards, and the power supplies are all accessible from the front. So if it was to be rack mounted in something that was, you know, the rack mounted up against a wall, it says repeatedly that it is useful for military applications. So I'm wondering, shipboard servers or something where the rack's fixed and you can only get to one side? I'm not certain, but that's the difference between the 4800 and the 4810. Okay, so starting with the center, the core, and I'm actually not going to start with the 6800. Instead, I'm going to start with the big kahuna, which I just bounced off the table. I'm trying not to pinch my fingers too bad. This is the center plane from the Sun E10000. So this is the big one. This is the board that it's supposedly 48 layers. It has an enormous block of aluminium underneath it to keep it rigid so that you don't flex it torsionally. And in 2001, 2002, to replace the center plane, it was $550,000 US. So this is a $500,000 board. Nowadays, of course, you can have them less, but they're usually sold in the $5,000 to $10,000 range. So I believe that I showed this in the last video of last year when I was taking things apart. So this is from the E10K that I got for spares. So on this side of the E10K, there's lots of noise. The other side is just a whole bunch of these connectors and then the aluminium block itself. Each of the connectors is for a system board. These connectors here are for the controller board and the center plane support board. And then we have row connectors for fans, things like that. The board is dominated with all of these heat sinks, and these are the system ASICs, the integrated controllers that handle the UPA bus that made the E10K so impressively fast. And I think it was maybe 6.8 gigabytes per second sustained, and it was peak at 100 and something gigabytes per second. So very powerful bus, huge amounts of logic on the center plane. So that would be why it was $500,000 when you cracked it. There was so much stuff on the center plane. The E10K was designed so that it was upgradable. So when faster processors came out, you could drop them onto the system board. If the processor architecture wasn't quite right, the system board actually came apart. And so the CPU bus, the board that was, could be replaced with another board, new CPUs on it. The center plane is designed to be replaced as well. And in reality, I don't believe that ever actually happened. They all used the same center plane. But it's heavily tied to upgradability, but with a huge amount of logic on the center plane. And in the 6800, the 4800, not the 3800, they went in a slightly different way. Pick this up. There's the big aluminium block, and it weighs every bit as much as you think it will. So this considerably daintier board is the center plane for the 6800, and you'll notice that there are a few things missing. This is the rear of the board, so we have our slots for our repeater boards. We've got the I/O cage connectors here, 1, 2, 3, 4. We've got a connector to control the system fans, DC-OK signals from the power supplies, all of that stuff. We've got bus bars, which are these big aluminium blocks here. So we've got 48 volt positive, negative, negative, positive. So the high amperage 48 volts that feed out of the power supplies are into here. And on the back side, well, there's not much at all, is there? We've got the 6 system board connectors. We've got the 2 system controller connectors, and then there's nothing else. It's just bare PCB. All of these little silver things are the connectors, or sorry, the through holes for the screws that mount this thing. I have to say, taking this thing apart was a delight. The engineers that designed the way that these things were assembled deserve every penny that they got. It took me all of 15 minutes to completely take this thing out. A third of that was taking all of the system board blanks, the system controllers, the I/O boxes, all of that stuff out and finding somewhere that I could put them without getting them damaged. 5 minutes to disconnect the bus bars, the cabling on the back, and then 5 minutes to undo the 19 freaking screws that hold this thing in here, and then it's just pop it out. It was delightful. Anyway, unlike the E10K one, which took me the better part of a day, the only thing that is particularly interesting on here is this little board here, which kind of hard to see. It's a separate DOTA board, and it contains a DC-DC converter for the 48 volts down to whatever the drive is, and the drive voltage that is, and it has an ID prompt so that it identifies the sender plane, and that's it. There is no logic on here. So all of the address bus and data bus ASICs that are on the E10K board, not here. So this is actually replaced with this, and there's not much here either. This is the repeater board for the mid-range system. In the 3800 for compactness, the ASICs that are on the system or on the repeater board are actually on the bus itself. The 4800s, 4810, the 6800s are separated like this. Mostly that was for packaging. So this is the repeater board. The repeater board is what's known as the L2 of the level 2 of the FirePlane Interconnect, which is the name of the bus that these systems use. We have a bunch of DC-DC converters for the 48 volts down. There's a little bit of logic, an ID prom, and that's it. There's not much on here. This board's primary job is when it gets a request in, it will determine which board it should go to and repeat it across the bus. There's just not too much to it. The address repeaters are set up in pairs, and you bit slice across them. So the address request is bit sliced across the repeater. With the 4800, you have 2 repeater boards, and if one of them fails, the system is down. You have to reboot the system to bring it back up, but it will run on a single board. With the 6800, you can separate it into 2 buses, and those are called platforms, and they are logically separate on board. So you can have an address repeater fail, you can have part of the center plane fail, I believe, and the other platform will continue ticking. Or you can have all 4 of them together, and it will form a single addressed repeater, which all of the requests are bit sliced off, and you get full throughput on the system. So where did all of that logic go? Most of it lies here. So this is the system board. It actually has a pair of covers on it normally. like this and like that. So the system board has most of the really scary clever stuff on it. The bus in the mid-ranges, the FirePlane, is designed for not only maximum throughput and resilience, certainly. They really want to be able to handle cache coherency and address snooping. So when you have a whole bunch of system boards, or a whole bunch of processors even, regardless of the architecture, and each processor effectively has local RAM. The RAM here is actually split up amongst the four processors, sorry. If you need a chunk of data for a process that's currently running in this processor here, but it's in RAM on a different CPU's chunk of RAM, or on a completely different system board somewhere else in the system, you need to know how to find that. And so the bus snooping and the cache coherency with directory level assist is how that's all accomplished. And it is remarkably complicated, and I understand probably half of it if I'm being generous for myself. But effectively, as the system is running, when it tries to do a data fetch, it uses a local address repeater and a local crossbar switch on the system board. So if it's on the system board, it can get it much quicker. But as it's doing it, it throws that address out onto the bus, which is what the repeater board's address repeater is for. And they get spread across so that all of the other system boards know where the RAM is that it's looking for. So if it looks for a chunk of data over here, and this CPU responds, that still goes off onto the bus so that a CPU however many boards away knows now that that chunk of data is here and it belongs to this CPU, and if it wants it, this is who it has to talk to. So it uses cache or bus snooping, where it uses the local RAM to keep track of what's going on the local bus, as well as the cache coherency, which is when you get to even larger systems, more and more processors, you need to have really detailed directory level structures of where the RAM is. And this is horribly simplified, and it's probably coming out wrong, but this is not a simple subject to understand. Anyway, but that is core to why this bus is so complicated and why there's so much stuff here. So we have 4 CPUs. On either side of the CPU are the eCache modules, which is the L2 RAM. So there's 64K of onboard L1 cache, and then there's 8 megs of offboard L2 cache, which is in the eCache slots. We've got a bunch of voltage regulators here. We've got a big DC-DC converter, smaller DC-DC converter. This here is the dual channel data switch. This is for the onboard data switching between the processors. It also handles sending on and off as well. So this is what makes inter-system board communication so ridiculously fast. And this is 9.6 gigabytes a second. And I think the peak is 192 gigabytes per second, which is astonishing. Then we have this side of the board. We have the boot bus ICs. We have the address repeater that's on board on this system board. We have the system data controller. And then we have the data controller chips, the data switch chips for the system as well. So you have the L1 of the FirePlane and the L2. And the L1 is handling all of the local data. It also handles the I/O bus interconnect. And then it fires it off to the L2, which is on the repeater board, that then blows it across all of the boards so that the bus snooping and the cache coherency can keep up. The base end system came with I believe it was a 450 megahertz UltraSpark 3. The top end was the 1200 megahertz UltraSpark 4. The boards look pretty much identical, but they are not, unfortunately, entirely compatible. The ID proms on here keep a flash image for the system when you slap in a new board, it will bring it up to the latest flash revision in the system. So if this is a brand new board and it's got a more recent flash image, the system won't boot, but from the system controller, you can copy the flash image across all of the systems and off it'll run. Unfortunately, and I think it's this board here, the flash image, no, because this is an UltraSpark 3, the flash, or the ID prom is busted, and so I can't actually update the flash image on it, it's corrupt. This is a 750 megahertz UltraSpark 3. The one that's got the bad ID prom is a 1.2 gigahertz UltraSpark 4, and I don't have any other boards that I can drop the CPUs on because all of them are UltraSpark 3 boards and they don't work. Each system takes up to 32 gigs of RAM, sorry, each system board. So that's a max of 192 gigs for the 6800. The RAM is split amongst the processors. It's interleaved across the banks, and one bank is for the first two processors and the other bank's for the second two. So if you only have two processors, you only have access to 16 gigs of RAM. The UltraSparks have RAM controllers, memory controllers built into the processor, which is kind of cool. I did read a nifty factoid that the UltraSpark 2 has, I think it's 2.9 million resistors or transistors in it, and these have 54 million. So a bit of a jump. So we have the system board, and we'll move it here and hopefully not crack it. We'll move next to the I/O. So we have the power supply for the system. So it'll generate the 3.3 volts, the 5 volts, and appropriate amperages for all the cards. We have 1, 2, 3, 4, 5, 6, 7, 8 slots. You'll see 6 of them are full length, 2 of them are half length. They're full 64-bit PCI slots. We've got some of the address and data repeaters on board. It's not that much to it. But with 4 of them between each system, that's 32 PCI boards per system, which is a reasonable amount of expandability. It gets cool when you get to this. This is the system controller, and this is what replaces the E10K's SSP. It has its own Spark processor on it. I believe it is a UltraSpark 2, but it's one of the mini Sparks or something. I forget the proper term for it. DC voltage. We've got the ID prom that has the information for the UltraSpark 2, MAC address, all of that crap. It's got flash RAM on board, which contains its own copy of the OS. When the system powers on and this gets voltage, this is the first thing that comes up. It'll post itself. It does basic rack post, AC, check the frame manager, things like that, make sure it's all copacetic. And then the system actually boots, and it boots VxWorks, and then it has a bunch of Java applications. It is Sun, of course it would be Java, that you then interact with. And so you have the domain controller, and then you have the you have the platform controller, and then you have the domain controller. So as I said before, the system can be split into 1 or 2 platforms, and they are logically separate, so that if you have a repeater board fail or something catastrophic happens, one platform may halt, the other one will keep on ticking, and so they are largely separated devices. You can also then subdivide them into 2 domains each. So with 2 platforms, 2 domains each. With 1 platform, it's 4 domains across the whole platform. A domain is not physically separated, but the operating system is separate. So you can assign, say you have 2 domains. You can assign half the system boards and half of the I/O card cages to one domain and the other half to the other. Both will run a separate copy of Solaris, and they are like 2 completely separate systems, 2 different computers running side by side. If this has a catastrophic failure, RAM completely goes crazy, the software goes nuts, takes the system out, this one runs on completely separately. Now in today's world of virtual machines, you know, where everybody has a half a dozen Zen instances, it's not quite so impressive, but cutting edge for this, and it is low level on the hardware, no hypervisor involved. The platform controller allows you to maintain the system as a whole. So you'd use that to set domain passwords, to tell it which system boards are up, add IO boards and things like that. You can also do a bunch of these things from the domain controller. In my case, I just have a single domain running, and when I bring the system up, comes up in the platform control, I switch the domain control, I do the physical key switch on, and then that'll bring the system up, and it'll join in all of the IO boards, system boards and things like that. From that area you can also say this system board's bad, don't use it, or this system board, the flash image is off, do a flash, make sure all the boards are the same level, things like that. Not having to have a Sun front end is great, and you know, what does it buy you? Probably not a whole heap. You still need, you know, a serial device to bring this thing up, although it will auto boot. You can have it do that, although it's not quite as cool as bring it up piece by piece by piece. But it's not a separate Ultra 5 front end, and so there's no, you know, software that you have to keep maintained and things like that. Everything's built into here, but it's still a separate piece of hardware, and so if the system controller fails, you have a problem. Now of course that's why each of them can have up to 2 system controllers, and that way if one fails the other one will take over. The master system clock, the bus on these runs at 150 megahertz, which I know doesn't sound like much, but the master clock for the system's on this board, so they are absolutely linked to this. If the system controller dies and you have a spare, it'll instantly hot swap, take it over. If it dies, you need to have access to it. The other one will allow you to get into the system. Anyway, I imagine this one's gone on long enough. These are the dull parts to it. I mean, it's exciting. I did have to chuckle at a comment from I believe a Russian commenter who said that the Sun was boring. It's not boring, it's cooler than hell. It's just newer. And possibly so unbelievably complicated that trying to grab it all in your brain's really not that easy. Anyway, so the guts of a SunFire 6800 mid-range server. Next time, we'll power one of them on. If you have been, thank you so very much for watching. I appreciate all of the comments. Take care, everybody.